constraining neutrino electromagnetic properties by germanium detectors. This is based on work in collaboration with myself. Michael.
Can you hear me? Today I'm talking about constraining neutrino electromagnetic forces. I'm talking about how to constrain neutrino electromagnetic properties by using germanium detectors. So what's the influence of the neutrino EM properties? These properties are the fundamental detectable properties. So this can be related to many interesting mechanics on list. So we may ask about, is there any non-zero very small mini charge carried by the neutrinos? If it does, then it must be the Dirac particle, not Majorana. So this is a interesting problem to search for. Another one is we know from this diagram, if we insert a mass turn in the extended model, this can lead to a small magnetic moment for the neutrinos. But from the experimental results, the upper bound for this properties is still much several of the enhancement than the model application. So this may be a problem to the new fields. So we are also interested in this. So here, this is the scaling diagram. And the neutrino is excited by the germanium atoms. So we see a complete set of electromagnetic form factors like this. And like Zhang's work, they are focused on the EDM, electron dipole moment, but we consider keeping the CT symmetry. So we are focused on the first two terms. They are also known as the Dirac form factor. And this is related to the charge, and this is related to the magnetic moment. Also, we have to mention that this term will conserve the spin. So this term will have interference with the weak intention. So you must be careful to deal with this. So for the atomic current part, now we know the neutrino magnetic moment and mini charge atomic ionization signal is much larger at low T, low energy transfer. So the atomic phase is important now. For current germanium detector, their detecting threshold now can be reduced to few 100 eV. So this is about the energy scale of atomic phase. What we can from the unit transfer, we know 1 Armstrong is about 1/2000 eV. So it means if our energy and momentum scale is about keV, then this photon, the wavelength of the virtual photon is about atomic length. From another point of view, electron momentum is about 3 keV. So we can know that if we want to go to lower to about few 100 eV, the atomic phase become much important. So we want to introduce an initial calculation for dealing with the atomic ionization. Here we're using NCRPA, which is multi-configuration related random phase approximation. So here I list an evolution for the evolution method. First, from the Hartree-Fock. Hartree-Fock is a method to solve the wave function self-consistently by reduce the many electrons to one electron with other mean field by other speculative electrons. And using variation principle to get a stable state. So we can use this to get an after wave functions. The next is RPA, which is including the electron hole pair isolation. This method treat the orbital state to time independent but oscillate with the perturbing external field. Then is the RPA is the relative form for RPA, which is much important when the atom number compare higher. Then the final one is NCRPA with more than one configuration. The configuration means that if we will have an open shell atoms, the open shell atom means that they are not full and balanced orbitals. So this energy gap between those the electrons in valence orbitals, well, this energy is much smaller than closed shell, so we cannot well distinguish from this ionization channel from the ground state. Like for germanium, there are two electrons in the outer shell, 4p. But if we consider they couple to the total G equals to 0, they have two configurations. One is both in the 4p 1/2. Another one is both in the 4p 3/2. So this energy gap is much smaller. So we have to notice the energy channel is from 4p 1/2 or from 4p 3/2. Okay, this is for more details. For time-dependent Hartree-Fock, we can step the wave function is the state determinant of all one electron orbitals like 1s, 2s, and we can invoke variation principle to get a stable state together, and then we can up the equation for those those one electron orbitals. And RPA is this time dependent to time dependent, but in expansion of power is not IOMT. Then MCRP is consider more than one configuration with their configuration weight. So this is a one-state structure of germanium. We have two configuration state, which is coupled to the whole G equals to 0. By multi-configuration Fock method, we can calculate the coefficient weight. So we can do the multiple expansion to G to the final state and our operates. Then by the selection rules, we can know all the possible transition channel from all orbitals. So as a benchmark, we have calculated the germanium photoionization first. So we can see above the ATEV, our calculation is good agreement with the exponential result. There are some problems in about 10 to ATEV, but let me because from the difference of the theoretical and experiment. Because it's using the germanium solid, but our calculation is for single atoms. So maybe some solid state effect against each region. But for the germanium decaying ratio, now it's still above 100 eV. So this our calculation may be still trustable. So in our published paper, we have shown two results from Sherman moment and mini charge. We can see our result can compare to two simple approximation. One is called FEA, which means free electron approximation. This method reduces the target by replaces the germanium target by a free electron with only a number of expanding energy. So we can so it's maybe a good approximation at high T, but for lower T, for lower energy transfer, the atomic effect become relevant. So the FGA should not be good at low T. It's still consistent with our result. For another one is called EPA. EPA is equivalent photon approximation, which treat the incoming neutrino as the equivalent real photon. But this real photon means that it's always transfer polarized and its energy equals momentum, so it will be only suitable at forward scattering in this case. So our result is much improvement from those two simple approximations. And these two results, we can see that it has big enhancement and low energy transfer compared to the standard model weak interaction background. So we can get a better. This is about the current upper bound for moment and mini charge. So we can see how these two channels are much obvious in about 100 eV. So this is we also collaborate with the Texano group, which their detectors putting near the Wosen nuclear power station, 核二厂. Their detector putting are putting near the power station to receive the electron anti-neutrino. The nuclear fusion neutrino spectrum is known, so we can do the calculation based on nuclear fusion neutrino spectrum. So this is their signals, and below two figures shows our theoretical calculation fitting with their data. So we can get some limit for determining moment and mini charge. We can see that mini charge we can compare with ordinary every year result. Our results.
1 minute.
Our results is a little worse because our calculation is much smaller and a little t. But for mini charge, we can get about 2 order improvement on this upper bound. So I go to the summary. Neutrino electron making more properties are proposed to a new phase. So in this work, we provide initial conclusion of germanium neutrino atomic ionization with about 5 to 10 errors. And then for another popular choice of detectors, xenon can be do as well. So this result can be set and upbound by comparing with experimental data. And in our ongoing project, we are trying to do a dynamic atomic annihilation trying to provide a theoretical input for those dark matter direct detection. Okay, here are my references, and thanks for your attention.
Questions? I have one comment. Could you go back to the summary table? Oh, yeah. For the you say FEA bond is stronger than the ab initio bond, right?
Yeah.
But the theoretical uncertainty in free electron approximation is actually bigger.
Yes.
So that's not a you cannot just look at the face value. All right. Okay, let's thank all the speakers for today. There's one more winner, Chen Weimin, who is visiting the Institute of Advanced Study at Princeton at the moment. So he won't be able to give a talk, and we also congratulate him. All right, thank you very much for coming, and that's the presentation for this year. Thank you.